So here's what we've done so far. So far, if you have some function up here, and we have a region down here, we talked about how we can divide the region, and we looked at one of these little rectangles, made a little parallelepiped. We had delta A sub k represented the area of one of these little rectangles. We took a point in the rectangle, I think it was in the middle, and we said x sub k star and y sub k star would be the coordinates of that point. So that up here, that mapped to a particular height. And taking the limit, as we increased the amount of these little parallelepipeds, gave us the volume under the surface. Okay, so I'm just kind of reviewing how we set that up. We're not going to get into a lot of the details, but we're going to argue that the process is going to be very similar if we were to try to figure out not having a region that we're integrating over, but having a solid that we're integrating over. Okay, so now we're going to have some solid that we're going to call G. So closed solid G. We say it's closed because it can be contained in a box. Okay, so here's G. So whereas before we said that this region R was closed as long as we could find some rectangular region that would, cover the entire thing, here's the same idea. We're just extending it one dimension further. So now we have a solid G. We say it's closed as long as we can find some box that would contain the entire solid. Okay. We're going to divide, G into n sub-boxes. So again, making the analogy of, instead of a little rectangle, we're going to partition this solid into n little boxes. So within the solid, there's going to be a little box. It looks kind of silly, but I'll zoom in. Now it looks more like a little box in there. Okay. And we're going to have n of those. And what we're going to do is denote the volume of the kth box not as delta A sub k, which was the area of the kth rectangle here. We're going to call the volume, what do you think would be appropriate here? Delta V sub k. And the point that's in the kth box, here we had just x sub k, y sub k because they were on the xy plane. Well, now this box may or may not be on the xy plane, or at least z-coordinate may not be. So the point will be x sub k star, y sub k star, and now we may have a z, sub k star. And the argument is going to be that if we take the limit as n goes to infinity, so now we're going to have an infinite amount of these little sub-boxes, and we add up all these little volumes, and multiply them with the function value, we get what we call not a double integral, but a triple integral over a solid region G of f of x, y, z dv instead of dA. Okay, so before, when we did double integrals, hopefully you remembered that we took the limit as n went to infinity of k equals 1 to n. We had f of x sub k star, y sub k star times delta a sub k. And we said that this represented a volume because we're taking area and multiplying it with what is this here? The height of one of these boxes, right? So taking a height with area, we get a bunch of little volumes. Well, now we're taking a volume and multiplying it with the output of the function, which is what we're going to say is a hypervolume. Now, this will have a bunch of real-world applications for us that we can actually conceptualize, visualize, and work with. But when you see these triple integrals and there's a bunch of stuff going on, I mean, this is really what's happening, is you're finding the volume of something that's not three-dimensional, but something that's larger. Okay? A 4D, yes. A 4D thing. Yes, that's exactly what's going on. Okay? As far as evaluating, though, not too bad. So we'll start off pretty easy. It's the same properties and evaluation methods as before. If the box, you know what, I shouldn't say if the box, if the solid G, so if G is a box defined by constants for x, so let's say x is between a and b, y is between c and d, and then z is between e and f, then the triple integral over that solid, over that box, bless you, is going to be evaluated however you want, really. Fubini's theorem says that as long as this region is a box, so instead of a rectangular region, now it's a box, we can do the order however we want. So if I did dz, dy, dx, then we just go e to f on the inner integral, c to d on the second one, and the one on the outside would be from a to b. And again, since these are all constants, the order in which you integrate is interchangeable, so you can switch it up if you want to, if it makes it easier. You're welcome to do that. Okay? Why don't we try an example? So let's say we're finding We're evaluating the triple integral of x, y, z squared dv, where g is defined by x, y, and z such that 0 is less than or equal to x, which is less than 1, negative 1 is less than or equal to y, which is less than 2, and 0 is less than or equal to z, which is less than or equal to 3. So here's our set notation for our bounds on x, y, and z. Since these are all constants, again, we can set them up however we want. Usually the convention is to go dz first, just like we like dy usually, unless there's a good reason to switch it. So I'll go z first, and then go dy dx. So z is from 0 to 3, y is from negative 1 to 2, and x is from 0 to 1. Okay, and again, you guys know how to do this. It's just one extra time that we have to integrate. When you integrate the first time, the integral of x, y, z squared with respect to z to x, y, z. Are you sure? You took the derivative. 2/3 x, y, or not 2/3. 1/3 x, y, z cubed. From 0 to 3, and that's for z. All right, so if we plug in 0 to 3, what do we get? You know what? I'm going to switch the order. Because I can.
Can I go this way? Can I go the other way?
Sure. Anybody know why I'm switching the order?
There's probably a logical reason.
Yes. Yes. Yeah, one term instead of two. That's exactly why I'm doing it, right? So now when we integrate with respect to x, that would be what? (9x squared y) from x equals 0 to x equals 1 dy. And again, this is why I chose to switch the order. If I plug in 0, that second term goes away, and now all that's left is 9 over 2y. Whoops, dy. Which, when you integrate, is 9/4 y squared from negative 1 to 2, which I'm going to sneak on this page. If you plug in the bounds, let's see, 4, 9 over 4, that's 36/4, so 9 minus 9/4. Bless you. Maybe I should have kept it as 36/4. 36 minus 9 is 27/4. Okay? Yeah. All right. Are we good with that? Because it's about to get pretty intense here. Just kidding. I'm just trying to scare you.
You're pretty close. We're about to walk.
Okay. Theorem. Let G be a simple solid with upper surface z equals g2 of xy, and lower surface z equals g1 of xy. Also, let R be the projection of G onto the xy plane. So this is the picture we're talking about. You have some upper surface, you have some lower surface, and now the solid G can be contained between these two surfaces. So here's our solid. So this is G. And now if you look from top down, this is going to create a shadow on the xy plane, which is what we mean by the projection. That little shadow is R. Okay, so using this setup, then we're going to say that the triple integral of a function f of x, y, z, dv, will be evaluated. First, we'll go, since we have clear bounds for z, lower bound for z, upper bound for z, we're going to say the integral is going to be integrated from g1 of xy to g2 of xy. So we're going to go dz first, take care of that, and then what's left on the outside? After we integrate once, what kind of integral is left? And what do we need to integrate? A double integral. A region or an area, R, and then now this becomes dA. So basically, once you integrate once, the rest of it is just like what we did before. Okay? So to find the limits, here's what I would do. Find upper and lower surfaces. Bounding G. 2. Make a 2D sketch of the projection R. Onto the xy plane. Treat this like usual. Okay, so once we get to this point, we treat this like usual. Once you have upper and lower surfaces bounding G, these are the limits. These are the limits for Z. Okay? Now, maybe what I'll do is just, instead of doing an example and then talking about how we can switch things around, let's just do that all now. So, in this scenario, we have a clear-cut, upper surface, lower surface. Here's our solid G. So it makes sense to integrate with respect to Z first. It could be possible that maybe it's a lot easier to identify surfaces that are not above and below, but maybe lateral surfaces. Does that make sense? So, for example, let's say we have so let's say that this is a completely vertical surface here, and so is this one. Like straight up and down. It's kind of hard to... You know what? I probably could do a better job of drawing that. Hold on. Let's say I did this.
Why are you still making a sign? Shouldn't it be like parallel with the z-axis if it's vertical?
These surfaces are.
Oh,
Vertical's that
it's
way.
this way.
Okay.
It's going along the x-axis.
Whoa, mine looks nothing.
Sorry, this is a bad picture.
Wait till this sort of
Bad. This is a better picture. And then somewhere back here... Okay, so do you guys see what I'm talking about? Like how this is a little different than this scenario here? Here we have a lower surface and an upper surface. Here we have, I don't know, a front surface and then a behind surface, if that makes sense. Okay? So then now instead of R being on the XY plane, where's R going to be? On the YZ plane. So somewhere back here is R. Okay? If that's the case, then the only thing that we're going to switch is how we integrate. What integral would I set up on the inside? Dx first. And then the bounds here would be from, here we have x equals, what would it be? A function of g1, actually let's make this g2, of what variables? Y and z. And then this will be x equals g1 of y and z. So then those are the bounds here. So we do this one first, and then the other one becomes a double integral over a region R. And then the other option, let me draw this a little slower. For some reason I just drew a typewriter, but we'll go with it.
Like that.
Thanks. I worked real hard on that this weekend.
We don't have to draw exactly what you want.
You can just draw a box.
Well, I drew something easier for last
The point is, the surfaces don't have to be like normal planes. They can be any surface, right? Okay, so now this is R back here. This is G, this whole thing. And now this surface will be G2, but it's a function of x and z. And then this one over here is a function of x and z, but we'll call it G1. So now instead of having lower or upper or forward and behind or backward. Here we have a left and right bound from our perspective. Okay? If that's the case, then the triple integral gets evaluated with respect to, this is what variable? Y first, so dy. And then we do dA, and then r, where r is the region, in this case, on the xz plane. Okay? So I'll do an example with you guys. I'll have you guys try one, and then we'll talk about volume.
You messed up your axes. What?
No.
What'd I do?
No, you got it. It's long. Which one did you send in?
Oh, okay.
Did I do the other one right? X equals, yes. Okay, no, I'm all right, I think.
You won.
Okay. Let's try an example. Let's do triple integral of z dv.
Is this a 2-dimensional?
No.
Oh,
Yeah.
I think it should be. It's going to be a long example.
No. Where T is the tetrahedron, bounded by x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. Okay. So, if I sketch this real quick, x, y, and z equaling 0 mean that essentially the coordinate planes are the boundaries. In addition, we have this plane with x, y, and z intercepts of 1 that cuts through, and this is how we get the tetrahedron. Okay, so let's. I always generally try to see if I can do it in z first. So if I'm looking in the z direction, is there a clear lower surface and then upper surface here?
No.
You sure?
Yes, there is. Z equals 0, Z equals 1.
Z equals 0, I agree with. Z equals 1 would be a plane that's kind of like that.
1 minus x minus y.
There you go. So if you get z alone here, 1 minus x minus y, that would be the upper surface.
Wait, so the surface doesn't have to be like parallel to the.
No, it does not.
Ah.
So we're going to say z is going from 0 to 1 minus x minus y. And then we just leave that alone for now. So z dz. And now if I'm looking to go dy dx, which I think is okay in this sense. So here's r, right? And if you can't see it from that picture, draw it in the normal 2 dimensions. Here's r, right? dy. So y is from y equals 0 to whatever this line is. What's the equation of that line? 1 minus x. Very good. And this is the point I need to make. On the outside, we always have what kind of bounds? Constants. So x is between 0 and 1. Okay, so for a triple integral, now that we've seen some more complicated ones, the inner 2 integrals may or may not have functions as their bounds. The outer one will always have constants as their bounds. Okay? Do you guys think you can handle the integration? Should we spend time maybe setting up some other ones?
Maybe
Or
some other one would be cool.
So, okay, so can we just do this and say that the answer is going to be 1 over 24? Okay,
Yeah.
That's what I got
awesome.
in my brain. Without doing it.
Okay. Let's do another one here. Triple integral of the square root of x squared plus z squared dv.
I'm not sure.
And let's say our solid is called E, and E is bounded by y equals x squared plus z squared, and y equals 4. So yeah, you got to remember some of your graphs. If you've forgotten, if you have a hard time, think about the normal. We're used to z equals, right? What z equals x squared plus y squared?
Cone.
It's not a cone.
It's a paraboloid.
It's a paraboloid, opening up, right? So here we're going to have a paraboloid, but instead of opening in the positive z direction, this is going to open in the positive y direction. So it's going to look something like this. And then here's our solid. My wife calls this the ham problem. I said, "What are you drawing a ham for?" I said, "What are you talking about? There's no ham."
That's awesome.
Y equals 4 is going to be right here. You guys understand that if I don't have to draw the entire y equals 4 plane, but if you slice through, you're just going to get a circle here, yeah?
No, could you draw the entire plane, please?
Sure.
He's kidding.
Now,
Let him do it. He's
well, maybe
You can't. That's like the...
not literally the entire plane, but I mean, here's what's going on.
He's gonna try.
No, you can't.
He's trying to carve the thing.
There it is. Now it's carved.
Well, no, I didn't actually.
It's more funny.
Okay. So now, back here is your region R, right?
Where's that look?
What shape is this?
Looks like a dreidel.
It's a circle.
I was thinking like the planet.
Now, if you're not sure what circle this is, we have the equation right up here because y equals 4 is going to be set equal to x squared plus z squared, right?
While you're shading, I don't have this many colors.
Right. I have
Sorry.
So that's...
Okay. So let's see if we can't set this up.
4 equals x squared plus z squared.
All right.
God bless you.
So now, I'm going to set this up. I think here we have a clear y upper bound, which is 4. Or a right bound, I guess. The lower bound would pretty much be this entire paraboloid, which is x squared plus z squared. So in the y direction, we're going to have something like this. And then we have dA. Let's kind of go a little more with this. So let's see. Maybe I go dz dx. So we'll keep this.
Oh.
So if we're going to go z,
Z equals root x.
1 minus x.
there you go. So the lower bound would be root of 4 minus the negative root of 4 minus x squared, positive root of 4 minus x squared,
Why is this so ugly? How are we supposed to do this?
negative 2 to 2. Do we understand how we set it up?
Yeah, you like get rid
Okay.
of y, right? You
Yeah.
make y equals 0 and then make the 2. Yeah.
Okay, so is this ugly? Yes. Does it get better? Yes. Let's keep going. So let's say I integrate the first time. With respect to y first, that just throws in a constant of y, right?
This equals 1.
And now here we're going to plug in our bounds, y equals x squared plus z squared, and y equals 4. So now we get negative 2 to 2, negative root of 4 minus x squared to positive root of 4 minus x squared. If you plug in 4 into the y, and then this, you're going to get 4 minus x squared minus z squared times the root of x squared plus z squared. dz dx. Do you guys see how I'm getting that?
I'm just writing what you're writing.
They,
I'm gonna be honest.
you're writing a lot of
Well,
stuff.
where are we confused?
You could
Oh,
have
I
a
get it.
simpler problem.
This is, well,
What?
this is a pretty
Alright.
simple problem.
Definitely leaving.
Are we clear on how I got this part?
Yeah.
How I got this one? Okay.
Yes.
Yeah, we still got time. Don't worry. Now, here's where we can make life a little easier. Why don't I convert to polar?
Oh, yeah, why not?
I mean, you can have fun integrating that. I'm going to switch this to polar.
Oh, good, you can do
Polar, oh, you're going to want to do polar. Or you're going to be here for a very long time.
I was wondering if you could.
Okay. We're going to do polar, but instead of in terms of x and y, it'll be in terms of
That weird.
x and z. Okay, so now instead of r equaling x squared plus y squared, or r squared equaling that, r squared will be x squared plus z squared. So this becomes, this becomes 4 minus what?
Okay. I was wondering.
R squared. The square root of x squared plus z squared is now just r. This becomes r dr d theta. And now our bounds, look back at the region. This was just a circle, right? So r is going from 0 to 2. And now theta, not with x, now it's spinning around the other axis, 0 to 2 pi. That's not a hard integral to
How'd you
do.
get 0 and 2?
Because this circle over here was a circle of radius 2. It's just instead of in terms of x and y, it's x and z.
Oh.
Does that make sense? Okay. And let's do this again. I think from here you guys are okay, right? 128 pi over 15 is what you're going to get.
You're not going to write this out.
One last thing and then we're done, okay?
An answer, I don't know. Okay, an answer, split line.
Volume,
Why couldn't you make this over 2 days?
because it's not meant to be over 2 days.
That's This is
volume as a triple integral. So when we did double integrals, we said, hey, we're finding volume under a function, and if we wanted to make this the area, the integrand became what? Just 1, right? Well, a triple integral works the same way. If you wanted to find the volume of a solid, instead of doing a double integral and having like a lower and upper surface, well, you wouldn't have that necessarily. I'm still in four-dimensional mode. The point I'm trying to make is that if you wanted to find the volume of a solid, you can use a triple integral and do the same concept that we did with double. Okay, that's it. Because you guys know how to, as long as you know how to set up the solid, then integrating 1 is easier than the stuff we've done.
How do you